Hey, welcome to our Night Scientists of the Universe. I'm so happy you're here with me today. There's something magical about taking a moment to pause, to breathe, and to explore the deeper mysteries that surround us every single day. Whether you're curled up in your favorite chair with a warm cup of tea, taking a quiet walk, or just finding a few minutes of peace in your busy day, I'm grateful we get to share this time together. You know, I've always found there's something deeply comforting about contemplating the big questions, those profound puzzles that have fascinated humans for thousands of years. Today, we're going to embark on a particularly extraordinary journey, one that will take us from the ticking of clocks in our everyday lives to the very edges of what science understands about reality itself. Today, we are diving into the fascinating world of what is time made of. This question might seem simple at first glance, but as we'll discover together, it opens up one of the most beautiful and mysterious territories in all of science. We'll explore how time isn't quite what it seems, how it behaves in ways that would have seemed like pure magic to our ancestors, and how modern physics has revealed that time itself might be constructed from something even more fundamental than we ever imagined. So settle in, take a deep breath, and let's begin this gentle exploration into one of the universe's most profound secrets. We'll take our time, after all. That's what we're here to understand. Close your eyes for a moment and listen to the world around you. Perhaps you can hear the gentle tick of a clock, the soft hum of traffic in the distance, or maybe just the quiet rhythm of your own breathing. Each of these sounds carries with it something invisible yet undeniably real, the flow of time itself. We live our entire lives immersed in time, like fish swimming in water, often barely conscious of its presence, until we stop to truly think about it. Every heartbeat marks another moment past. Every sunrise brings a new day. Every breath is a small journey from one instant to the next. But what exactly is this mysterious current that carries us all forward? For most of human history, time seemed straightforward enough. The sun rises and sets, the seasons change, we age and grow older. Time appeared to be like a great river, flowing steadily from past to future, carrying everything along with it at the same unchanging pace. Ancient philosophers and early scientists pictured time as absolute and universal, a cosmic clockwork that ticked away the same for everyone, everywhere in the universe. Isaac Newton, that gentle giant of physics, imagined time as flowing like a perfect stream, uniform and consistent throughout all of creation. In his mind, if you could somehow step outside the universe and watch it like a cosmic movie, you would see time flowing at exactly the same rate everywhere on Earth, on distant stars, in the vast emptiness between galaxies. A second here was a second there, a minute was a minute, an hour was an hour, no matter where you were or how fast you were moving. This view of time felt natural and comforting. It matched our everyday experience perfectly. When we make plans to meet a friend, we assume we're both experiencing time at the same rate. When we watch a movie, we expect it to unfold in a predictable sequence. When we remember the past or imagine the future, we think of these as distinctly different realms, separated by the flowing present moment. But as we'll discover, this intuitive picture of time as a simple, steady river is just the beginning of a much more extraordinary story. Modern physics has revealed that time is far stranger, far more flexible, and far more mysterious than Newton or anyone else could have imagined. Time, it turns out, is not the rigid framework we thought it was, but something that can stretch and compress, that can be woven together with space itself. And that might not even be fundamental at all. The first hints that time might be more complex than we thought, came from an unexpected direction. In the late 1800s, scientists were puzzling over the nature of light. They knew light was a wave, but waves need something to wave through. Water waves need water, sound waves need air. So what did light waves need? They imagined an invisible substance called the ether that filled all of space, providing the medium through which light could travel. But when scientists tried to measure Earth's motion through this ether, something strange happened. No matter how they set up their experiments, no matter which direction they pointed their instruments, they always got the same result. The speed of light was constant. This was puzzling because it meant that light didn't behave like other waves. If you're on a train moving toward a sound source, you hear the sound at a higher pitch because you're moving toward waves. But light didn't work this way. It always traveled at the same speed, relative to the observer. Regardless of how fast the observer was moving, this peculiar behavior of light was like discovering that no matter how fast you run toward or away from a river, the water always flows past you at exactly the same speed. It didn't make sense according to the physics of the time, but the experiments were clear and consistent. Something fundamental about our understanding of space and time was about to change. What scientists didn't realize at the time was that they were bumping up against one of the universe's most profound secrets, that space and time are not separate, independent entities, but are woven together into a single fabric that can bend, stretch, and twist in ways that would revolutionize our understanding of reality itself. Imagine you're floating in a vast, dark ocean on a perfectly calm night. The water stretches endlessly in all directions, smooth as glass, reflecting the stars above. Now imagine that this ocean is not made of water, but of something far more subtle and mysterious, an invisible fabric that weaves together all of space and all of time into a single unified whole. This is space-time, and it's perhaps the most beautiful and profound discovery in all of physics. The person who first glimpsed this hidden fabric was Albert Einstein, and his insight came from wrestling with that puzzling behavior of light we just discussed. Einstein was a gentle soul with wild hair and a curious mind, someone who loved to take long walks and think deeply about the nature of reality. He had a gift for seeing the world in a completely new way, and his vision of space-time changed everything. We thought we knew about the universe. Einstein realized that the constancy of light speed wasn't just a curious experimental result. It was a fundamental clue about the nature of space and time themselves. If light always travels at the same speed, regardless of how fast you're moving, then something else must be changing to make this possible. That something, Einstein realized, was time itself. Picture two people, Alice and Bob, passing each other in space. Alice is sitting quietly in her spaceship, while Bob zooms by at tremendous speed. From Alice's perspective, Bob appears to be moving very fast. But here's the strange part. From Bob's perspective, he's sitting still, and Alice is the one who's moving. This is the principle of relativity. There's no absolute standard of rest in the universe. Motion is always relative to the observer now. Both Alice and Bob shine flashlights and measure the speed of light. According to our everyday intuition, the light from Bob's flashlight should appear to be moving faster to Alice because Bob is moving toward her. But that's not what happens. Both Alice and Bob measure exactly the same speed of light. The universe ensures this by doing something extraordinary. It adjusts the flow of time itself. Time, Einstein realized, flows more slowly for objects moving at high speeds. This isn't just a theoretical curiosity, it's a real, measurable effect. From Alice's perspective, Bob's clocks are running slow. Bob ages more slowly, his heartbeat is slower, even his thoughts unfold at a more leisurely pace. But from Bob's perspective, everything seems normal. It's Alice whose clocks are running slow. This stretching and compressing of time is called time dilation, and it's one of the most mind-bending aspects of Einstein's special theory of relativity. The faster you move through space, the slower you move through time. At everyday speeds, this effect is incredibly tiny, barely measurable. But as you approach the speed of light, time dilation becomes dramatic. Imagine Bob decides to take a trip to a nearby star at 99% the speed of light. From Alice's perspective, Bob's journey takes about 4 years to the star and 4 years back, for a total of 8 years. But due to time dilation, Bob's clocks run much slower. When he returns, he might find that only 1 year has passed for him, while Alice has aged 8 years. This is the famous twin paradox. The traveling twin returns younger than the one who stayed home, but Einstein's insights went even deeper. He realized that just as fast motion affects time, so does gravity. In fact, gravity and acceleration are intimately connected. You can't tell the difference between being accelerated upward and being pulled downward by gravity. This led Einstein to his general theory of relativity, which revealed that gravity is not a force pulling on objects, but rather a curvature in the fabric of space-time itself. Picture that smooth ocean we imagined earlier, but now imagine heavy objects placed on its surface, just as a bowling ball would create a depression in a stretched rubber sheet. Massive objects like stars and planets create curves and valleys. In the fabric of space-time, what we experience as gravity is actually objects following the curved paths through this warped space-time. This curvature of space-time affects time in beautiful and profound ways. The stronger the gravitational field, the slower time flows. If you could somehow stand on the surface of a neutron star, an object so dense that a teaspoon of its material would weigh about 1 billion tons, time would pass noticeably slower for you than for someone floating in empty space far away. This is gravitational time dilation, and it's happening to us right now. Though the effect is tiny, the GPS satellites orbiting Earth experience this effect. They're farther from Earth's gravitational field than we are, so their clocks run slightly faster than ours. Without accounting for this time dilation, GPS would quickly become inaccurate. The satellites have to continuously adjust their clocks to stay synchronized with Earth-based time. A daily reminder that Einstein's insights about the nature of time are not just theoretical curiosities, but practical realities. What's truly remarkable is that space-time is not just a passive stage on which events unfold, but an active participant in the cosmic drama. Space-time can ripple and wave, carrying information about cosmic events across vast distances. When two black holes spiral into each other billions of light-years away, they create ripples in space-time that eventually reach Earth as gravitational waves, actual distortions in the fabric of space and time that we can now detect with incredibly sensitive instruments. Now, as we venture deeper into the nature of time, we must leave behind the familiar world of planets and stars, of rockets and GPS satellites, and enter a realm that exists all around us, but remains largely invisible to our everyday experience. This is the quantum realm, where reality behaves in ways that would seem like pure magic if we encountered them in our daily lives. In the quantum world, particles can exist in multiple places at once. they can be connected across vast distances in mysterious ways, and they can tunnel through barriers that should be impossible to cross. But perhaps most intriguingly for our exploration, the quantum realm offers tantalizing clues about what time itself might be made of at the deepest level. To understand how time behaves in the quantum realm, we need to first appreciate just how strange this microscopic world really is. Imagine you could shrink down to the size of an atom and explore the interior of a hydrogen atom, the simplest atom in the universe. You might expect to find a tiny solar system with an electron orbiting around a proton like a miniature planet around a sun. But that's not what you would find at all. Instead, you would discover something far more mysterious. The electron doesn't orbit the proton in a well-defined path. Instead, it exists in a kind of ghostly cloud of probability, sometimes called an electron cloud or orbital. The electron is, in a very real sense, spread out over this entire region simultaneously. It's not that we don't know where the electron is. It's that the electron genuinely doesn't have a definite location until something forces it to choose one. This fundamental uncertainty is not just a limitation of our measuring instruments or our knowledge. It's a basic feature of reality itself, enshrined in what physicists call the uncertainty principle. This principle tells us that certain pairs of properties, like position and momentum, or energy and time, cannot be measured simultaneously with perfect precision. The more precisely you try to measure one, the less precisely you can know the other. When it comes to time, this uncertainty principle has profound implications. It suggests that at the quantum level, time itself becomes uncertain, fuzzy, probabilistic, just as an electron doesn't have a definite position until it's measured. Quantum events don't have perfectly definite times until they're observed. Time, at its most fundamental level, appears to be subject to the same quantum uncertainty that governs everything else in the microscopic world. This quantum nature of time becomes most apparent when we consider the shortest possible time interval. That has physical meaning. This is called the Planck time, named after Max Planck, one of the founders of quantum theory. The Planck time is unimaginably brief, about 10 to 43 seconds. To put this in perspective, there are more Planck time intervals in a single second than there are seconds in about YP years. The entire age of the universe is only about YY seconds at the Planck timescale. Our usual concepts of space and time begin to break down completely. Space and time become so uncertain, so quantum, that they lose their familiar, smooth, continuous character. Instead, they become grainy, foamy, discontinuous. Physicists sometimes call this the quantum foam, a seething, bubbling froth of space and time that exists at the smallest scales of reality. In this quantum foam, space and time don't flow smoothly like a river, but rather behave more like a turbulent ocean during a storm. Virtual particles constantly pop into existence and annihilate each other. Tiny wormholes might open and close, and the very fabric of space-time fluctuates wildly. It's a realm where the familiar laws of physics give way to something more fundamental and more mysterious. But here's where things get really interesting for our exploration of what time is made of. Some physicists believe that time itself might be an emergent property, something that arises from more fundamental processes, rather than being fundamental itself. Just as the wetness of water emerges from the behavior of individual water molecules, time might emerge from the collective behavior of something even more basic. One intriguing possibility is that time is constructed from quantum entanglement, the mysterious connection that can exist between quantum particles. When two particles become entangled, they remain connected in a way that defies our everyday understanding of reality. Measure one particle, and you instantly know something about the other, even if they're separated by vast distances. Einstein famously called this spooky action at a distance, but it's a real phenomenon that has been verified in countless experiments. Some theoretical physicists propose that the networks of quantum entanglement that permeate the universe might be the fundamental building blocks from which space-time itself is constructed. In this view, space and time don't exist independently, but rather emerge from the complex web of quantum connections that link all particles in the universe. Time, in this picture, would be a measure of how these quantum connections evolve and change. Another fascinating possibility involves what are called time crystals, a recently discovered state of matter that seems to violate our usual understanding of time. Normal crystals, like salt or diamond, have a regular, repeating structure in space. Time crystals have a regular, repeating structure in time. They oscillate between different states in a regular pattern, even when they're in their lowest energy state, their quantum ground state. What makes time crystals so intriguing is that they seem to create their own rhythm of time. They tick away like cosmic clocks, but their ticking emerges from the quantum properties of matter itself, not from any external timekeeper. This suggests that time might not be imposed on the universe from outside, but rather might be generated by the universe itself through quantum processes. These ideas are still at the cutting edge of theoretical physics, and we're far from understanding their full implications. But they point toward a radical possibility, that time as we know it might be like the surface of a deep ocean. We see the waves and the currents, we feel the rhythm of the tides, but beneath the surface lies something far more fundamental and mysterious, as we'll explore further in our journey. This quantum nature of time opens up extraordinary possibilities for understanding not just what time is made of, but why it behaves the way it does, why it seems to flow in only one direction, and how it connects to the deepest mysteries of consciousness and existence itself. For now, let's take a moment to appreciate the profound mystery we're encountering. Time, which seems so familiar and straightforward in our everyday lives, turns out to be one of the most complex and beautiful aspects of reality. It's woven together with space, it's affected by motion and gravity, it's uncertain at the quantum level, and it might even be constructed from something more fundamental than we ever imagined. As we continue our gentle exploration, we'll discover even more surprising aspects of time's nature, and we'll begin to see how these discoveries might change our understanding of what it means to exist in this magnificent universe. Have you ever wondered why you can remember the past but not the future? Why a broken vase doesn't spontaneously reassemble itself? Why we age instead of growing younger? These questions all point to one of the most profound mysteries in physics, the arrow of time. While the fundamental laws of physics are mostly reversible, our universe clearly has a preferred direction through time. An understanding why reveals some of the deepest secrets about what time is truly made of. Picture yourself watching a movie of everyday life played in reverse. You would see some truly peculiar things: water flowing upward from the sink back into the faucet, smoke descending from the sky and condensing into a cigarette, people walking backward with perfect coordination. While these reversed scenes would be perfectly consistent with the basic laws of physics, they would seem utterly wrong to us because they violate our deep intuition about the direction of time. This directional quality of time is what physicists call the arrow of time. and it's one of the most beautiful and mysterious aspects of our universe. Unlike space, which has no preferred direction, you can move north or south, east or west, with equal ease. Time seems to have a definite orientation. Events flow from past to future, never the other way around. But here's the truly puzzling thing. Most of the fundamental laws of physics are time-symmetric. If you look at the equations that describe how particles move, how electromagnetic fields behave, or how quantum systems evolve, they work equally well whether time is running forward or backward. The laws of physics don't seem to care about the direction of time, yet our universe clearly does. This creates what physicists call the problem of time's arrow. If the fundamental laws are time-symmetric, why does our universe have such a clear preference for one direction of time? It's like discovering that while the rules of a game allow players to move in any direction, everyone always chooses to move in the same direction. There must be something special about the initial conditions or the environment that creates this preference. The answer, it turns out, lies in one of the most fundamental concepts in physics: entropy. Entropy is often described as a measure of disorder, but it's more subtle than that. It's really a measure of the number of different microscopic ways that a system can be arranged while still looking the same macroscopically. A tidy room has low entropy because there are relatively few ways to arrange the objects so that everything looks neat and organized. A messy room has high entropy because there are many ways to scatter the objects around, while still maintaining the same overall level of messiness. The second law of thermodynamics tells us that in an isolated system, entropy tends to increase. Over time, this might seem like a simple statement, but it has profound implications for the nature of time itself. The second law gives us a thermodynamic arrow of time. Entropy provides the direction that distinguishes past from future. Think about what happens when you drop a sugar cube into a cup of coffee. Initially, the sugar is highly organized. All the sugar molecules are clustered together in a neat cube. But as time passes, the sugar dissolves and spreads throughout the coffee. The sugar molecules become randomly distributed, reaching a state of maximum entropy. You would never expect to see the reverse process: sugar molecules spontaneously organizing themselves back into a cube. This process illustrates the deep connection between entropy and time's arrow. The sugar cube dissolves because there are vastly more ways for the sugar molecules to be randomly distributed throughout the coffee than there are for them to be organized into a cube. The system naturally evolves toward the state with higher entropy, not because there's a law forcing it to, but simply because high entropy states are overwhelmingly more probable than low entropy states. This probabilistic nature of entropy is crucial to understanding time's arrow. Imagine you have a box with a partition in the middle. On one side, you have a gas compressed into a small volume. On the other side, you have empty space. When you remove the partition, the gas expands to fill the entire box. This expansion happens because there are many more ways for the gas molecules to be distributed throughout the entire box than there are for them to remain crowded in one corner. The remarkable thing is that this process is irreversible not because of any fundamental law, but because of probability. In principle, all the gas molecules could spontaneously move back to one side of the box. But this would require an extraordinarily unlikely coincidence. Every single molecule would have to happen to move in exactly the right direction at exactly the right time. While this isn't impossible, it's so improbable that it would never occur in practice. This connection between entropy and probability gives us a statistical arrow of time. The future is the direction in which entropy increases, not because entropy must increase by law, but because increases in entropy are overwhelmingly more probable than decreases. Time's arrow emerges from statistics, from the simple fact that there are more ways to be disordered than ordered. But this raises another deep question. If entropy always increases, why was the entropy of the universe so low in the beginning? The early universe was in a state of extraordinarily low entropy. Everything was smooth, uniform, and highly organized. If entropy always increases, how did the universe start in such a special low-entropy state? This is one of the most profound questions in cosmology. The answer seems to lie in the nature of gravity and the initial conditions of the universe. Unlike other forces, gravity becomes stronger as things clump together. When matter is spread smoothly throughout space, it has low gravitational entropy. But as gravity pulls matter together into stars, planets, and galaxies, it creates the complex, hierarchical structure we see in the universe today. The early universe was indeed in a state of low entropy, but this was gravitational low entropy. Everything was smooth and uniform. As the universe evolved, gravity pulled matter together, creating the cosmic structures we observe today. This gravitational clumping increased the entropy of the universe, providing the arrow of time that we experience. But gravity's role in time's arrow goes even deeper. When stars form and begin to shine, they convert nuclear fuel into energy and heat. This process creates entropy on a massive scale. The organized nuclear fuel is converted into random heat and light that spreads throughout space. The universe is filled with starlight, and this radiation represents an enormous increase in entropy compared to the original smooth distribution of matter. Eventually, all the stars will burn out, all the fuel will be exhausted, and the universe will reach a state of maximum entropy called heat death. In this far future state, everything will be at the same temperature, no more energy will be available to do work, and the arrow of time will effectively disappear. The universe will have reached thermodynamic equilibrium, and without entropy, gradients to drive change, time itself will lose its meaning. This connection between entropy and time's arrow has profound implications for our understanding of what time is made of. It suggests that time's directional quality isn't fundamental, but rather emerges from the statistical behavior of matter and energy. The arrow of time is a consequence of the universe's journey from low entropy to high entropy, from order to disorder, from the organized simplicity of the early universe to the complex equilibrium of the far future. As we journey deeper into the nature of time, we encounter some of the most cutting-edge ideas in theoretical physics, ideas so revolutionary that they challenge our most basic assumptions about the nature of reality itself. These theories suggest that space-time, including time, might not be fundamental at all, but rather might emerge from something even more basic and mysterious. One of the most intriguing approaches to understanding the deep structure of space-time comes from a theory called loop quantum gravity. This theory proposes that if we could zoom in to the smallest possible scales of space and time, scales much smaller than atoms, smaller than protons, smaller than anything we can directly observe, we would find that space-time itself is not smooth and continuous, but rather is made up of discrete, quantized units. Imagine looking at a photograph from a distance. It appears to be a smooth, continuous image with flowing curves and gradual transitions between colors. But if you look closely enough, you begin to see that the photograph is actually made up of individual pixels. discrete points of color that, when viewed together, create the illusion of a continuous image. Loop quantum gravity suggests that space-time might be similar, smooth, and continuous at the scales we can observe, but fundamentally discrete at the smaller scales. In this theory, space is not empty void, but rather is made up of incredibly tiny loops, quantum loops of space itself. These loops are unimaginably small, existing at the Planck scale we discussed earlier. Time, in this picture, emerges from the way these loops evolve and change, just as a movie is made up of individual frames that create the illusion of continuous motion. Time might be made up of discrete moments that create the illusion of continuous flow. These spatial loops are connected to each other in a vast network that physicists call a spin network. Think of it like a cosmic web, but instead of galaxies and dark matter, it's made up of the fundamental building blocks of space itself. The geometry of space-time emerges from the pattern of connections in this network, and time emerges from the way this network evolves. What makes this picture so fascinating is that it suggests space and time don't exist independently, but rather emerge from something more fundamental, the network of quantum relationships that connect these elementary loops. In this view, asking what time is made of is like asking what a song is made of. The song isn't made of physical material, but rather emerges from the pattern of relationships between individual notes, the timing of their appearance, and the way they connect to create melody and harmony, another revolutionary approach to understanding. Space-time comes from string theory, which proposes that the fundamental building blocks of reality are not point particles, but rather tiny, vibrating strings. These strings are incredibly small. If an atom were the size of the Earth, a string would be about the size of a tree. The different ways these strings can vibrate correspond to different particles and forces in our universe. In string theory, space-time itself might be emergent, arising from the collective behavior of these fundamental strings. Time, in this picture, would be a measure of how the strings vibrate and interact with each other, just as the sound of a violin emerges from the vibrations of its strings. Time might emerge from the cosmic symphony of all the strings in the universe. But perhaps the most radical idea about the nature of space-time comes from the holographic principle. This principle suggests that all the information contained in a volume of space can be encoded on the boundary of that space. It's like discovering that everything happening inside a sphere can be completely described by information written on the surface of the sphere. The holographic principle emerged from studies of black holes, those mysterious objects with gravitational fields so strong that nothing, not even light, can escape from them. Physicists discovered that the amount of information that can be stored in a black hole is proportional not to its volume, but to the area of its surface. This suggests that what we think of as three-dimensional space might actually be encoded in a two-dimensional surface. If the holographic principle is correct, then our three-dimensional reality, including time, might be a projection from a more fundamental two-dimensional reality. Time, in this picture, would be like the motion you see in a hologram. It appears real and three-dimensional, but it's actually encoded in a lower dimensional surface. This idea has led to a fascinating connection between quantum mechanics and gravity called ADS-CFT correspondence. This connection suggests that certain quantum field theories that describe the behavior of quantum particles, are mathematically equivalent to theories of gravity in higher dimensions. In other words, gravity and space-time might be different ways of describing the same underlying quantum reality. What makes this connection so profound is that it suggests space-time itself might be an emergent property of quantum entanglement. Quantum entanglement is the mysterious connection that can exist between quantum particles. Measure one particle, and you instantly know something about another particle, even if they're separated by vast distances. Recent research suggests that the networks of quantum entanglement that permeate the universe might be the fundamental building blocks from which space-time is constructed. In this picture, space and time don't exist independently, but rather emerge from the complex web of quantum connections that link all particles in the universe. The geometry of space-time would be determined by the pattern of these quantum connections, and time would be a measure of how these connections evolve and change. This idea is still highly speculative, but it points toward a radical conclusion: that time, space, and even gravity might not be fundamental features of reality, but rather might be emergent properties of something more basic. The quantum information that describes the state of the universe. Another approach to understanding the fundamental nature of space-time comes from causal dynamical triangulation, CD. This theory attempts to construct space-time from the ground up, using simple geometric building blocks, triangles in 2 dimensions, tetrahedra in 3 dimensions, and their higher dimensional analogues. The idea is to start with these simple geometric pieces and glue them together according to certain rules to create a model of space-time. The fascinating thing is that when physicists run computer simulations of this process, they find that the resulting space-time naturally develops the familiar 4-dimensional structure. We observe 3 dimensions of space and 1 dimension of time. What makes CDT particularly interesting for understanding time is that it treats time differently from space. While space can be curved and distorted in various ways, time maintains a clear directional structure. This built-in asymmetry between space and time might explain why time has an arrow while space doesn't. In CDT, time emerges from the way the geometric building blocks are connected. The theory suggests that, at the smallest scales, time might be discrete rather than continuous, made up of individual moments rather than flowing smoothly. Time would be like the frames of a movie, creating the illusion of continuous motion from a series of discrete snapshots. All of these theories, loop, quantum gravity, string theory, holographic principle, and causal dynamical triangulation, point toward a common conclusion that space-time, including time, might not be fundamental. Instead, they suggest that time emerges from more basic processes: quantum networks, vibrating strings, holographic encoding, or geometric construction. This is a profound shift in our understanding of reality. For centuries, we thought of space and time as the stage on which the drama of physics unfolds. But these new theories suggest that space and time might be part of the drama itself, emergent properties of deeper, more fundamental processes. As we explore the deepest mysteries of what time is made of, we must also turn our attention to a question that's deeply personal and intimately familiar. How do we, as conscious beings, experience time? The nature of our temporal experience, the way we perceive the flow of moments, the way we remember the past and anticipate the future, offers profound clues about the nature of time itself. Consider this moment, right now, as you read these words. You have a clear sense of now, a feeling that this moment is somehow special, somehow different from the past moments you remember or the future moments you anticipate. This sense of now is so fundamental to our experience that it's hard to imagine consciousness without it. Yet this feeling poses a deep puzzle for our understanding of time. if time is truly what Einstein's relativity tells us it is, a dimension woven together with space in the fabric of space-time, then there should be no universal now. Different observers, moving at different speeds or in different gravitational fields, should disagree about what events are happening now, and indeed, this is exactly what relativity predicts. The now that you experience is not the same as the now experienced by someone moving at high speed relative to you. This leads to what physicists call the block universe interpretation of time. In this view, all moments past, present, and future exist equally. Time is like a vast landscape that we can only see one part of at a time, but the entire landscape exists simultaneously. Our sense of moving through time is like driving through a countryside. We can only see the immediate surroundings, but the entire countryside exists, even though we can't see it all at once. If the block universe is correct, then our perception of time's flow is a kind of illusion created by our consciousness. We experience time as flowing because consciousness has the unique ability to create a sense of now, to carve out a special moment from the eternal block of space-time. But this raises profound questions about the nature of consciousness itself. How does consciousness create this sense of now? Why do we experience time as flowing rather than simply existing? Some researchers suggest that our perception of time's flow is intimately connected to memory and anticipation. We remember the past because our brains store information about previous states, and we anticipate the future because our brains can model possible outcomes. This creates the psychological experience of time as a journey from remembered past through experienced present to anticipated future. But memory itself is a deeply mysterious process. When you remember something, you're not simply accessing a stored file like a computer retrieving data. Instead, you're reconstructing the memory from fragments of information scattered throughout your brain. Each time you remember something, you're essentially creating a new version of that memory, influenced by your current state of mind and subsequent experiences. This reconstructive nature of memory means that your sense of the past is not a fixed record, but rather a dynamic creation of your present consciousness. The past, as you experience it, is constantly being recreated in the present moment. This suggests that our psychological arrow of time, our sense of moving from past to future, is not simply a reflection of the physical arrow of time, but rather is actively constructed by our consciousness. The connection between consciousness and time becomes even more intriguing when we consider altered states of consciousness. People who have experienced certain types of meditation, psychedelic experiences, or mystical states often report profound changes in their perception of time. Time might seem to slow down, speed up, or even stop entirely. Some report experiencing past, present, and future as simultaneously accessible, or feeling as though they exist outside of time altogether. These altered states suggest that our ordinary perception of time is not fixed or inevitable, but rather is one possible way that consciousness can organize temporal experience. The fact that time perception can be so dramatically altered suggests that the flow of time, as we experience it, is not a direct reflection of the physical nature of time, but rather is a construction of consciousness. Neuroscientists are beginning to understand some of the brain mechanisms that create our perception of time. Different types of temporal experience, the sense of duration, the perception of temporal order, the feeling of temporal flow, seem to involve different brain networks. The brain appears to have multiple clocks that operate at different timescales, from the millisecond timing involved in speech perception to the circadian rhythms that govern sleep and wakefulness One fascinating aspect of brain timing is that it's not passive like a mechanical clock, but rather is actively constructed by neural activity. The brain doesn't simply measure time, it creates time. The duration of an experience is not just determined by how long it lasts in physical time, but also by how much neural activity it generates. This is why time seems to slow down during emergencies or speed up when we're having fun. The brain's construction of time is also deeply connected to attention and consciousness. When we pay attention to something, we're not just focusing our awareness, we're also creating a temporal structure for that experience. Attention carves out moments from the continuous flow of neural activity, creating the discrete experiences that make up our conscious lives. This suggests that consciousness might play a fundamental role in creating the very structure of time as we experience it. Just as quantum mechanics suggests that measurement plays a role in creating the physical properties of particles, consciousness might play a role in creating the temporal properties of experience. Some philosophers and scientists have proposed that consciousness might even be necessary for time to exist at all. In this view, time is not something that exists independently of conscious observers, but rather is created by the very process of consciousness itself. The universe might be filled with potential moments, but these moments only become actual through the process of conscious observation. This idea connects to some of the deepest questions in quantum mechanics about the role of observation in creating reality. If consciousness plays a fundamental role in quantum mechanics, and if time is ultimately quantum mechanical, then consciousness might be one of the basic ingredients from which time is constructed. Another fascinating aspect of consciousness and time is the way that different types of conscious experience seem to exist in different temporal modes. When you're deeply absorbed in a creative activity, time seems to disappear. You might look up and discover that hours have passed without your noticing. When you're bored or anxious, time seems to crawl by slowly. When you're in a state of flow or meditation, the usual sense of temporal progression can fade away entirely. These different temporal modes suggest that there might not be a single, universal way that consciousness experiences time. Instead, consciousness might have multiple ways of organizing temporal experience, each adapted to different types of activities and states of mind. The ordinary sense of linear time progression might be just one of these modes, useful for practical activities like planning and coordination, but not necessarily the deepest or most fundamental way of experiencing temporality. As we continue our exploration of what time is made of, we must keep in mind that any complete understanding of time must account for both its physical and experiential aspects. Time is not just something that exists out there in the universe, it's also something that we experience in here in our consciousness. The deepest understanding of time will likely require bridging these two perspectives, understanding how the physical processes that create time connect to the conscious processes that experience it. As we venture deeper into the mystery of what time is made of, we discover that one of the most profound insights comes from an unexpected source: the theory of information. It turns out that time and information are intimately connected in ways that reveal some of the deepest secrets about the nature of reality itself. To understand this connection, let's start with a simple question. What is information? At its most basic level, information is about distinguishing between different possibilities. When you flip a coin, you're gathering information about which of two possibilities, heads or tails, has occurred. When you read a book, you're processing information that distinguishes between different arrangements of letters and words. When you look at a sunset, you're receiving information about the colors and patterns of light that distinguish this particular sunset from all other possible sunsets. This might seem like a simple concept, but information theory reveals that information is far more fundamental than we might initially think. Information is not just something that exists in books or computers. It's woven into the very fabric of reality itself. Every quantum particle carries information about its state. Every interaction between particles involves the exchange of information, and even empty space itself might be filled with information. The connection between information and time becomes apparent when we consider what happens when information is processed or transmitted. Every time information changes or moves from one place to another, it takes time. This isn't just a practical limitation, it's a fundamental principle of physics. Information cannot be transmitted faster than the speed of light, and quantum information cannot be copied perfectly. These limitations create deep connections between the flow of information and the flow of time. Consider what happens when you send a message to a friend. The information in your message, the particular arrangement of letters and words, must travel through space to reach your friend. This journey takes time, and the amount of time depends on the distance the information must travel and the speed at which it can be transmitted. In a very real sense, the flow of information creates a kind of temporal structure. Events that are connected by information flow have a definite temporal order. This connection between information and time becomes even more profound when we consider quantum mechanics. In the quantum world, information is not just about what we know about a system, it's about what the system knows about itself. When quantum particles interact, they exchange information about their states. This exchange of information creates correlations between the particles, and these correlations evolve over time in precise, predictable ways. Quantum entanglement provides a particularly striking example of how information and time are connected. When two particles become entangled, they share quantum information in a way that creates an instantaneous correlation between their states. If you measure one particle and find it spinning clockwise, you instantly know that the other particle is spinning counterclockwise, even if it's on the other side of the universe. But here's the fascinating part. While the correlation between entangled particles is instantaneous, the information about this correlation cannot be transmitted faster than light. You can't use entanglement to send a message to someone far away, because the information about what you've measured only becomes available when the measurement results are communicated through normal channels that are limited by the speed of light. This creates a subtle but profound distinction between correlation and communication, between the sharing of quantum information and the transmission of classical information. Entangled particles share quantum information instantaneously, but the classical information about their states must still flow through space and time at the speed of light. Some physicists believe that this distinction between quantum and classical information might be fundamental to understanding what time is made of. The flow of classical information through space creates the temporal structure that we experience as the passage of time. The quantum information that is shared instantaneously through entanglement might exist in a more fundamental realm that underlies our ordinary experience of time. This idea connects to some of the most cutting-edge theories in physics. The holographic principle, which we discussed earlier, suggests that all the information in a volume of space can be encoded on the boundary of that space. If this is true, then space and time might be emergent properties of the way information is organized and processed. In this view, what we experience as the three-dimensional world with its flowing time is really a projection from a more fundamental two-dimensional reality where information is encoded. Time, in this picture, emerges from the way information is processed and organized on this two-dimensional surface. The idea that time might be made of information has profound implications for our understanding of causality, the way that events influence each other. In our everyday experience, causality seems straightforward. Causes precede effects, and effects follow causes. But in a universe where time is made of information, causality might be more subtle and complex. Consider what happens when you make a decision. From your perspective, you think about various options, weigh their pros and cons, and then choose a course of action. This process seems to unfold in time, with your thoughts and considerations preceding your decision. But if time is made of information, then the decision process might be more like a computation, a processing of information that creates the outcome. In this view, the temporal sequence of thoughts leading to a decision might be more like the logical sequence of steps in a computation. The decision isn't caused by the preceding thoughts in the way that a ball is caused to move by being hit with a bat. Instead, the decision emerges from the processing of information, just as the output of a computer program emerges from the processing of data. This information-theoretic view of time also sheds light on the arrow of time that we discussed earlier. We saw that time's arrow is connected to the increase of entropy, the tendency of systems to evolve towards states of greater disorder. But entropy is actually a measure of information, specifically. It's a measure of the information required to specify the detailed state of a system. When a system has low entropy, it means that knowing a few key pieces of information allows you to predict the detailed state of the entire system. A perfectly ordered crystal has low entropy because knowing the position of one atom allows you to predict the positions of all the other atoms. A gas at high temperature has high entropy because you need to know the position and velocity of every individual molecule to fully specify its state. The second law of thermodynamics, which says that entropy tends to increase, is really a statement about information. It says that systems tend to evolve toward states where more information is required to specify their detailed configuration. This increase in information requirements creates the arrow of time that we experience. But this raises a deep question. Where does this information come from? If the universe is constantly generating new information as entropy increases, what is the source of this information? Some physicists suggest that the answer lies in the quantum mechanical process of measurement. When a quantum measurement occurs, it creates new information about the state of the system being measured. Before the measurement, the system exists in a superposition of multiple possible states. After the measurement, it has a definite state, and this definiteness represents new information that didn't exist before. The universe is constantly creating new information through the process of quantum measurement, and this creation of information drives the arrow of time. This idea connects to some of the deepest questions in quantum mechanics about the role of observation in creating reality. If consciousness plays a role in quantum measurement, and if quantum measurement creates the information that drives time's arrow, then consciousness might play a fundamental role in creating the temporal structure of reality. Another fascinating aspect of the connection between information and time is the way that information can be used to seemingly violate the second law of thermodynamics. This is illustrated by a famous thought experiment called Maxwell's demon. Imagine a tiny being that can observe individual molecules in a gas and open or close a door between two chambers based on the velocities of the molecules. The demon could sort fast molecules into one chamber and slow molecules into the other, creating a temperature difference without doing any work at first glance. This seems to violate the second law of thermodynamics, which says that heat can't spontaneously flow from cold to hot. But the resolution lies in the information processing performed by the demon. The demon must observe the molecules to determine their velocities, and this observation process requires energy and generates entropy. When you account for the information processing, the total entropy of the system still increases, preserving the second law. This example illustrates a deep principle. Information has a thermodynamic cost. Every bit of information that is processed or erased requires a minimum amount of energy and generates a minimum amount of entropy. This connection between information and thermodynamics is called the Landauer principle, and it suggests that information is not just abstract data, but has real physical consequences. The Landauer principle has profound implications for our understanding of time. If information processing has a thermodynamic cost, then every computation, every thought, every observation contributes to the increase of entropy in the universe. The flow of information through space and time is not just a passive description of what happens. It's an active process that drives the evolution of the universe. This connects to an intriguing possibility that consciousness itself might be a kind of information processing system that plays a fundamental role in creating time. When we observe the world, when we form memories, when we make decisions, we're processing information in ways that contribute to the arrow of time. Our consciousness might not just experience time, it might help create it. Some researchers have proposed that the universe itself might be a kind of vast information processing system, a cosmic computer that computes its own evolution. In this view, what we experience as the passage of time is really the universe computing its next state based on its current state. The flow of time is the flow of computation, and the arrow of time is the direction in which the computation proceeds. This computational view of time has fascinating implications for questions about free will and determinism. If the universe is computing its own evolution, then the future is not predetermined in a simple sense. It's computed based on the current state of the universe. This computation might include random elements from quantum mechanics, making the future genuinely unpredictable, even in principle. But the computation also includes the information processing performed by conscious beings. When we make decisions, we're contributing to the universe's computation of its own future. In this sense, we're not just passive observers of time. We're active participants in its creation. As we continue our exploration of what time is made of, we must venture into one of the most beautiful and mysterious realms of physics, the world of quantum fields. These fields represent the deepest level of reality that we currently understand, and they reveal that time itself might be a dynamic, fluctuating phenomenon that emerges from the quantum dance of the universe. To understand quantum fields, we need to radically change our picture of what exists at the most fundamental level. Instead of thinking of the universe as made up of tiny particles moving through empty space, we need to imagine it as filled with invisible fields that permeate all of reality. These fields are not like any fields we encounter in everyday life. They're quantum fields, subject to the strange rules of quantum mechanics. Imagine space itself as a vast ocean, but instead of water, it's filled with quantum fields. Just as The ocean's surface can have waves of different sizes and intensities. These quantum fields can have fluctuations and excitations. What we think of as particles, electrons, photons, quarks, are actually localized excitations in these underlying fields. Like waves on the quantum ocean, the quantum field for electrons fills all of space. And what we call an electron is really a ripple in this field. The photon field fills all of space, and what we call a photon is a ripple in this field. Every type of particle corresponds to its own quantum field, and all of these fields are constantly fluctuating and interacting with each other. But here's where things get really interesting for our understanding of time. These quantum fields don't exist in time, they are time. The fluctuations and interactions of quantum fields are what create the temporal structure of reality. Time emerges from the quantum dance of these fundamental fields. This idea becomes clearer when we consider what happens in the quantum vacuum, the state of lowest energy where no particles are present. You might think the vacuum is empty, but it's actually filled with quantum field fluctuations. These fluctuations are constant and unavoidable. They're a fundamental feature of quantum mechanics. Even when no particles are present, the quantum fields are still fluctuating, creating virtual particles that pop into existence and annihilate each other in incredibly short time intervals. These vacuum fluctuations are not just theoretical curiosities, they have real, measurable effects. They create a tiny force called the Casimir effect, where metal plates placed very close together in a vacuum are pushed toward each other by the pressure of quantum field fluctuations. They also contribute to the anomalous magnetic moment of the electron, a quantity that has been measured to extraordinary precision and matches theoretical predictions based on quantum field theory. The fascinating thing about vacuum fluctuations is that they exist everywhere and at all times. There's no such thing as truly empty space. Everywhere is filled with the constant fluctuations of quantum fields. These fluctuations create a kind of quantum foam at the smaller scales of space and time, where the usual concepts of smooth, continuous space-time break down. At the Planck scale, the smaller scale at which our current theories make sense, space and time become granular and discontinuous. The quantum field fluctuations become so intense that they create virtual black holes, wormholes, and other exotic structures that constantly appear and disappear. The smooth fabric of space-time that we experience at larger scales emerges from this seething quantum foam. This suggests that time, at its most fundamental level, is not smooth and continuous, but rather is made up of discrete, quantized units. Just as matter is made up of atoms, time might be made up of tiny, indivisible moments, quantum moments, that exist at the Planck scale. The quantum nature of time becomes even more apparent when we consider how quantum fields interact. When two quantum fields interact, they exchange virtual particles, quantum fluctuations that carry energy and momentum between the fields. These virtual particles don't exist in the same way as real particles. They exist only for the brief moment of the interaction, and they obey a different set of rules. The exchange of virtual particles creates forces between real particles. The electromagnetic force between charged particles is mediated by virtual photons. The strong force between quarks is mediated by virtual gluons, and the weak force is mediated by virtual W and Z bosons. Even gravity, according to quantum field theory, should be mediated by virtual gravitons, though we haven't yet developed a complete quantum theory of gravity. What's fascinating about virtual particles is that they exist in a kind of temporal limbo. They're allowed to borrow energy from the quantum vacuum as long as they pay it back quickly enough. The amount of energy they can borrow and the time they can exist are related by the uncertainty principle. The more energy they borrow, the shorter their lifetime must be. This creates a picture of time as a dynamic, fluctuating phenomenon. At the quantum level, time is not a smooth flow, but rather a complex dance of virtual particles appearing and disappearing, borrowing energy from the future and repaying it to the past. The arrow of time emerges from the statistical properties of these quantum fluctuations. The quantum nature of time also has profound implications for our understanding of causality. In classical physics, cause and effect are clearly ordered in time. Causes precede effects. But in quantum field theory, the relationship between cause and effect becomes more subtle and complex. Virtual particles can, in a sense, travel backward in time. When a virtual particle is created, it can be thought of as a real particle traveling forward in time and an antiparticle traveling backward in time. This doesn't violate causality because the virtual particle doesn't carry information. It's just a mathematical description of the quantum interaction. But this backward time travel of virtual particles creates fascinating possibilities. Some physicists have proposed that retrocausality, the idea that future events can influence past events, might be a real phenomenon in quantum mechanics. This doesn't mean that you can send messages to the past, but it might mean that the quantum state of the universe at any given moment depends on both past and future influences. This idea connects to some of the deepest mysteries in quantum mechanics, such as the quantum measurement problem. When a quantum measurement is performed, the wave function of the system appears to collapse instantaneously, regardless of the size of the system. This collapse seems to violate the principle that information cannot travel faster than light. Some interpretations of quantum mechanics suggest that this instantaneous collapse is possible because the quantum state of the universe is determined by both past and future boundary conditions. The measurement doesn't just reveal the state of the system, it helps determine the state of the system retroactively. Time, in this picture, is not a one-way street, but rather a complex network of quantum correlations that extend both forward and backward. The quantum field picture of time also suggests that time might be emergent rather than fundamental, just as temperature emerges from the collective behavior of atoms, time might emerge from the collective behavior of quantum fields. The smooth, continuous time that we experience at macroscopic scales might be a statistical approximation to the underlying quantum reality. This emergence of time from quantum fields is still a highly speculative idea, but it's supported by some fascinating theoretical work. Some researchers have shown that in certain quantum field theories, the concept of time can be derived from more fundamental quantities like entanglement and information. In these theories, what we call time is really a measure of how much quantum entanglement has been created between different parts of the universe. As the universe evolves, quantum interactions create more and more entanglement, and this increasing entanglement defines the arrow of time. The future is the direction in which entanglement increases, and the past is the direction in which entanglement decreases. This entanglement-based picture of time has profound implications for our understanding of the universe. It suggests that time is not an external parameter that describes the evolution of the universe, but rather is an internal property of the universe itself. The universe doesn't evolve in time, it evolves time. The quantum field picture of time also sheds light on some of the deepest questions in cosmology. If time emerges from quantum fields, then the beginning of time, the Big Bang, might be understood as the emergence of quantum fields from a more fundamental, timeless state. Some cosmologists have proposed that the universe began in a state of quantum superposition, where all possible histories existed simultaneously. The arrow of time emerged as this superposition evolved into the definite history that we observe. In this picture, the Big Bang was not the beginning of time in an absolute sense, but rather the beginning of the particular timeline that we inhabit. This quantum field picture of time is still highly speculative, and we're far from a complete understanding of how time emerges from quantum fields. But it represents one of the most promising approaches to understanding the deepest nature of time itself. As we near the end of our journey into the nature of time, we must consider one of its most remarkable and mysterious aspects: its creative power. Time is not just a passive dimension through which events unfold. It's an active participant in the creation of novelty, complexity, and beauty in the universe. Consider the incredible journey that has brought us to this moment. Billions of years ago, the universe was a hot, dense soup of elementary particles. There were no atoms, no molecules, no stars, no planets, no life. Yet through the passage of time, this simple beginning has blossomed into a cosmos of breathtaking complexity and beauty. Stars have formed and died, creating the heavy elements that make up planets and life. Galaxies have grown and evolved, creating vast structures that span millions of light years on at least one planet, and possibly many others. Life has emerged and evolved into forms of incredible complexity and intelligence. Through time, the universe has become not just more complex, but more interesting, more beautiful, more meaningful. This creative power of time is not just a consequence of the laws of physics. It's built into the very nature of time itself. Time creates the possibility for novelty, for the emergence of new forms and patterns that have never existed before. Without time, there would be no evolution, no development, no creativity. But what is the source of this creative power? Why does time seem to have a natural tendency to create complexity and beauty? The answer lies in the subtle interplay between order and chaos, between determinism and randomness that characterizes the flow of time. On one hand, time is governed by precise mathematical laws. The laws of physics determine how particles move, how forces interact, how energy flows. These laws are deterministic. Given the current state of a system, they precisely predict its future state. This deterministic aspect of time creates order and predictability. On the other hand, time is influenced by quantum randomness. At the quantum level, events are not precisely determined, but rather occur with certain probabilities. This randomness creates an element of unpredictability in the flow of time. The future is not completely determined by the past. There's always room for surprise, for the unexpected, for the genuinely new. The creative power of time emerges from the delicate balance between these two aspects. Pure determinism would create a universe that is completely predictable and unchanging. Pure randomness would create a universe that is completely chaotic and meaningless. But the actual flow of time combines both elements, creating a universe that is both ordered and surprising, both predictable and creative. This balance between order and chaos is what allows complex structures to emerge and evolve. Consider the formation of a star. The process begins with tiny, random fluctuations in the density of gas in space. These fluctuations are amplified by gravity, which pulls matter together according to precise mathematical laws. As the gas collapses, it heats up and eventually ignites nuclear fusion, creating a star. The star's life is a delicate balance between the inward pull of gravity and the outward pressure of nuclear fusion. This balance is maintained by precise feedback mechanisms that adjust the rate of fusion based on the star's temperature and pressure. Eventually, the star exhausts its nuclear fuel and undergoes dramatic changes. It might explode as a supernova, creating and dispersing heavy elements throughout space. This entire process is a beautiful example of time's creative power. Random fluctuations are organized by deterministic laws to create complex, beautiful structures. The process is neither purely random nor purely deterministic. It's a creative synthesis of both. The same principle applies to the evolution of life. Random mutations provide the raw material for evolutionary change, but natural selection organizes these mutations according to the deterministic logic of survival and reproduction. The result is the incredible diversity and complexity of life on Earth. Even in our own lives, we can see the creative power of time at work. Our personalities, our relationships, our achievements are all the result of the complex interplay between chance and choice, between the random events that happen to us and the decisions we make in response to those events. Time creates the possibility for growth, for learning, for becoming more than we were before. This creative aspect of time is closely connected to the arrow of time that we discussed earlier. The second law of thermodynamics tells us that entropy tends to increase over time. But this increase in entropy is not just about the creation of disorder. It's also about the creation of new possibilities. As entropy increases, the universe explores new states that it has never been in before. Each moment is unique, never to be repeated. This constant creation of novelty is what drives the evolution of the universe from simple beginnings to complex, beautiful structures. The creative power of time also manifests in the realm of consciousness. Our consciousness exists in time. We experience a continuous flow of thoughts, feelings, and perceptions. This temporal flow is not just a passive experience, it's an active process of creation. When we remember the past, we're not just accessing stored information, we're actively reconstructing our memories, influenced by our current state of mind and our subsequent experiences. When we imagine the future, we're not just predicting what will happen, we're creating new possibilities that didn't exist before. Our consciousness is constantly creating new meaning, new connections, new understanding. We take the raw material of experience and transform it into stories, insights, and wisdom. This creative process is fundamentally temporal. It unfolds in time and creates something new that didn't exist before. Some philosophers have suggested that consciousness and time are intimately connected, that consciousness is time and time is consciousness. In this view, the flow of time is not something that happens to consciousness, it's something that consciousness creates. Our experience of temporal flow is not just a passive observation of the universe, it's an active participation in its creation. This creative aspect of time has profound implications for how we understand our place in the universe. We're not just passive observers of cosmic evolution, we're active participants in it. Our consciousness, our choices, our creativity are all part of the universe's ongoing process of self-creation. When we create art, when we solve problems, when we love, we're continuing the creative work that time has been doing since the beginning of the universe. We're part of the cosmic process by which simple beginnings give rise to complex, beautiful, meaningful realities. This perspective gives our lives a cosmic significance that goes beyond our individual existence. We're not just temporary arrangements of matter and energy. We're active participants in the universe's creative evolution. Our actions, our thoughts, our experiences are all part of the ongoing creation of novelty and meaning in the cosmos. The creative power of time also suggests that the future is genuinely open. If time is truly creative, then the future is not simply a predetermined consequence of the past. Instead, the future is being created moment by moment through the ongoing process of temporal evolution. This doesn't mean that the future is completely unpredictable. The laws of physics still provide constraints on what can happen. But within those constraints, there's genuine creativity, genuine novelty, genuine freedom. The future is not a fixed destination that we're traveling toward. It's a creative process that we're participating in. Understanding time's creative power can profoundly change how we live our lives. Instead of seeing ourselves as victims of circumstances beyond our control, we can see ourselves as co-creators of the future. Instead of being passive observers of life, we can be active participants in its unfolding. This creative aspect of time is perhaps what makes it so precious. Time is not just a resource to be consumed or a burden to be endured. It's an opportunity to participate in the universe's ongoing creation of beauty, meaning, and value. Every moment is a chance to add something new to the cosmos, to contribute to the ongoing evolution of reality itself. As we continue our gentle exploration of what time is made of, we must pause to consider a fascinating paradox. Time is perhaps the most precisely measured quantity in all of physics, yet it remains one of the most mysterious. The story of how we measure time reveals profound insights about the nature of time itself, and it points toward some of the deepest questions in modern physics. For thousands of years, humans have sought to measure time with ever-increasing precision. We began with sundials and water clocks, moved to mechanical clocks with pendulums and springs, and eventually developed atomic clocks that can measure time with extraordinary accuracy. Today's atomic clocks are so precise that they would lose less than a second over the entire age of the universe. But what exactly are we measuring when we measure time? This question might seem trivial at first, but it opens up a profound mystery. When we measure distance, we're comparing one length to another. When we measure mass, we're comparing one weight to another. But when we measure time, what are we comparing? What is the fundamental standard against which all other durations are measured? The answer, surprisingly, is vibration. All of our most precise clocks are based on regular, repeating oscillations. Pendulum clocks use the regular swing of a pendulum. Quartz clocks use the regular vibration of a quartz crystal. Atomic clocks use the regular oscillation of electromagnetic radiation, absorbed or emitted by atoms. This reliance on oscillation reveals something profound about the nature of time. Time, it seems, is not measured by comparing it to some external standard, but rather by counting the regular repetitions of some cyclical process. In a very real sense, time is rhythm. It's the beat that underlies all of existence. But this creates a puzzle. If time is measured by oscillation, then what determines the rate of oscillation? Why does a cesium atom vibrate at exactly 9,192,631,770 times per second? Why not some other frequency? The answer lies in the fundamental constants of physics: the speed of light, the charge of the electron, Planck's constant, and other quantities that seem to be built into the fabric of reality itself. These fundamental constants are not arbitrary choices. They're deeply connected to the structure of space and time. The speed of light, for example, is not just the speed at which light travels, it's the speed at which information can propagate through space-time. Planck's constant determines the scale at which quantum effects become important. These constants are, in a sense, the fundamental rhythms of the universe. This suggests that time might be even more fundamental than we might have initially thought. Time is not just a dimension through which events unfold. It's the very foundation of the rhythms that make existence possible. The vibrations of atoms, the oscillations of electromagnetic fields, the quantum fluctuations of the vacuum, all of these are expressions of time's fundamental nature. But the measurement of time also reveals another profound mystery, the problem of simultaneity. When we say that two events happen at the same time, what exactly do we mean? Einstein's relativity tells us that simultaneity is relative. Events that are simultaneous for one observer may not be simultaneous for another observer moving at a different speed. This relativity of simultaneity has profound implications for our understanding of time. It suggests that there is no universal now, no moment that is simultaneous for all observers throughout the universe. Instead, each observer has their own personal timeline, their own sequence of now, moments that may not align with the timelines of other observers. This creates a puzzle for our understanding of time's passage. If there's no universal now, then in what sense does time flow? The block universe interpretation suggests that all moments exist equally, and that our sense of time's passage is a kind of illusion created by consciousness. But this interpretation raises profound questions about the nature of change and becoming. Another mystery revealed by the measurement of time is the discrete nature of temporal experience. While our clocks can measure time continuously, our consciousness seems to experience time in discrete moments. We don't experience a continuous flow of awareness. Instead, we experience a series of discrete moments of consciousness, each lasting perhaps a fraction of a second. This discreteness of conscious experience might reflect a deeper discreteness in time itself. Just as matter is made up of discrete atoms, time might be made up of discrete moments, quantum units of time that cannot be subdivided further. This idea connects to some of the most advanced theories in physics, which suggest that space-time itself might be quantized at the smallest scales. The measurement of time also reveals the intimate connection between time and energy. Every process that can be used to measure time, from the swing of a pendulum to the vibration of an atom, requires energy. Time measurement is not a passive observation, but an active process that requires the expenditure of energy. This connection between time and energy is enshrined in the uncertainty principle, which tells us that energy and time are complementary variables. The more precisely we try to measure the timing of an event, the more uncertain we become about the energy involved. This suggests that time and energy are not separate quantities, but rather different aspects of the same underlying reality. The uncertainty principle also reveals another profound aspect of time, its quantum nature. At the quantum level, time itself becomes uncertain and probabilistic. Events don't happen at precise moments, but rather within probability distributions of possible times. This quantum uncertainty of time is not just a limitation of our measurement capabilities, it's a fundamental feature of reality itself. This quantum nature of time has profound implications for our understanding of causality in classical physics. Cause and effect are clearly ordered in time. Causes precede effects. But in quantum mechanics, the relationship between cause and effect becomes more subtle and complex. Quantum events don't have precise times, so the order of cause and effect can become ambiguous. Some interpretations of quantum mechanics suggest that the future can influence the past in subtle ways that don't violate causality. This retrocausality doesn't allow us to send messages to the past, but it might mean that the quantum state of the universe at any given moment depends on both past and future influences. The measurement of time also reveals the connection between time and consciousness. Our perception of time is not just a passive observation of an external flow, it's an active construction created by our brains. Different states of consciousness create different perceptions of time, and these perceptions can be dramatically altered by various factors. When we're absorbed in an interesting activity, time seems to fly by. When we're bored or in pain, time seems to crawl. When we're in emergencies or dangerous situations, time seems to slow down. These changes in time perception are not just psychological. They reflect real changes in the way our brains process temporal information. The brain's construction of time is a complex process that involves multiple neural systems operating at different timescales. Some systems track millisecond timing for activities like speech and music. Others track circadian rhythms for sleep and wakefulness. Still, others track longer-term patterns for memory and planning. This multiplicity of time systems in the brain suggests that time is not a single, unified phenomenon, but rather a complex construction that emerges from the interaction of multiple processes. Just as color is not a single property, but rather a construction created by the interaction of different wavelengths of light, time might be a construction created by the interaction of different rhythms and cycles. The measurement of time also reveals the deep connection between time and information. Every clock is, in essence, an information processing system. It takes in information about some regular process and outputs information about the passage of time. The precision of the clock depends on the regularity of the process and the accuracy of the information processing. This connection between time and information suggests that time might be fundamentally informational in nature. Just as space might be emergent from quantum entanglement, time might be emergent from information processing. The flow of time might be the flow of information, and the arrow of time might be the direction in which information complexity increases. As we delve deeper into the nature of time, we inevitably encounter one of the most fascinating and perplexing questions in all of physics. Is time travel possible? This question, which has captured the imagination of scientists and storytellers alike, reveals profound insights about the nature of time itself and the fundamental structure of reality. The possibility of time travel is not just science fiction. It's a serious topic of study in theoretical physics. Einstein's relativity tells us that time is not absolute but relative, and that the passage of time can be affected by motion and gravity. This opens up tantalizing possibilities for manipulating the flow of time and potentially traveling to different moments in the past or future. We've already discussed how time dilation works, how fast motion and strong gravitational fields can slow down the passage of time. This is actually a form of time travel to the future. If you travel at very high speeds or spend time in a strong gravitational field, you will age more slowly than someone who remains at rest in weak gravity. When you return, you will have traveled into their future. This kind of time travel to the future is not just theoretical, it's been observed and measured. Particles called muons created in the upper atmosphere by cosmic rays, have very short lifetimes and shouldn't be able to reach the Earth's surface. But because they're moving at very high speeds, time dilation extends their lifetimes enough for them to reach the ground. From our perspective, they travel into the future. GPS satellites experience time dilation because they're moving at high speeds and are farther from Earth's gravitational field. Their clocks run about 38 microseconds per day faster than clocks on Earth. This might seem like a tiny amount, but it's enough to make GPS significantly inaccurate if not corrected. The satellites are essentially traveling into the future at a rate of about 38 microseconds per day. But what about traveling to the past? This is where things get really interesting and really strange. General relativity does allow for solutions that would permit travel to the past, but they require exotic conditions that may not be possible in our universe. One possibility is shortcuts through space-time that could connect different points in space and time. If you could create a wormhole and manipulate its ends using time dilation, you might be able to create a time machine. But wormholes would require exotic matter with negative energy density, which may not exist in nature. Another possibility is closed time-like curves, paths through space-time that loop back on themselves. If you could follow such a path, you would return to your own past. Some solutions to Einstein's equations, like the Gödel metric and the Kerr solution for rotating black holes, do contain closed time-like curves, but these solutions require very special conditions that may not occur in our universe. The most famous proposed time machine is the Alcubierre drive, which would create a warp bubble in space-time. Inside the bubble, space-time would be flat and normal, but outside the bubble, space-time would be warped in such a way that the bubble could travel faster than light. This wouldn't violate relativity because nothing inside the bubble would move faster than light relative to the local space-time, but like wormholes, the Alcubierre drive would require exotic matter with negative energy density. And even if such matter exists, the energy requirements would be enormous, possibly greater than the energy contained in the entire observable universe. The possibility of time travel to the past raises profound paradoxes that challenge our understanding of causality and logic. The most famous is the grandfather paradox. If you travel back in time and prevent your grandfather from meeting your grandmother, how could you have been born to travel back in time in the first place? There are several proposed solutions to this paradox. One is the Navikov self-consistency principle, which suggests that the universe would conspire to prevent any paradox from occurring. If you tried to kill your grandfather, something would always happen to prevent you from succeeding. The universe would be self-consistent. Any action you took in the past would be consistent with the future you came from. Another solution is the many worlds interpretation, which suggests that traveling to the past would create a new timeline or parallel universe. You wouldn't be traveling to your own past, but rather to a different version of the past. This would avoid paradoxes because the timeline you came from would remain unchanged. A third solution is the bootstrap paradox, which suggests that information or objects can exist in a causal loop with no origin. For example, if you travel back in time and give Shakespeare a copy of Hamlet, and Shakespeare then publishes it as his own work, where did the play originally come from? This paradox suggests that causality might be more complex than we usually think. These paradoxes reveal deep questions about the nature of time and causality. If time travel to the past is possible, then our usual understanding of cause and effect might be incomplete. The universe might be more strange and complex than we imagine, with causal loops and bootstrap paradoxes as natural features of reality. But perhaps the most profound insight from studying time travel is what it reveals about the nature of time itself. The fact that relativity allows for time travel to the future, but makes time travel to the past extremely difficult, suggests that time might have a fundamental asymmetry built into it. This asymmetry is connected to the arrow of time that we discussed earlier. The second law of thermodynamics tells us that entropy tends to increase over time, creating a preferred direction for temporal evolution. This thermodynamic arrow of time might be what makes time travel to the past so difficult. It would require reversing the natural tendency of entropy to increase. The study of time travel also reveals the deep connection between time and information. If you could travel to the past and change something, you would be creating new information that didn't exist before. This might violate fundamental principles of information conservation, suggesting that the universe has built-in mechanisms to prevent temporal paradoxes. Some physicists have proposed that quantum mechanics might provide a natural mechanism for preventing time travel paradoxes. The uncertainty principle tells us that quantum events are inherently probabilistic, and this probabilistic nature might make it impossible to create deterministic paradoxes. Even if you could travel to the past, the quantum nature of reality would make it impossible to predict or control the exact outcomes of your actions. The possibility of time travel also raises profound questions about free will and determinism. If the future already exists and can be visited, then it seems that the future is already determined. But if you can travel to the past and change it, then the future must be malleable and open to change. These contradictory implications suggest that our usual concepts of time and causality might be incomplete. Perhaps the most important insight from studying time travel is that it forces us to think more deeply about the nature of time itself. Time travel scenarios reveal the assumptions we make about time and causality, and they challenge us to develop more sophisticated understanding of temporal reality. Even if time travel to the past turns out to be impossible, the study of time travel has already contributed to our understanding of time. It has revealed the deep connections between time and space, time and gravity, time and information, and time and consciousness. It has shown us that time is not the simple, uniform flow that we might have imagined, but rather a complex, dynamic aspect of reality that is intimately connected to the deeper structures of the universe. As we approach the culmination of our gentle journey into the nature of time, we must grapple with perhaps the most profound questions of all. Did time have a beginning? Will it have an end? These questions touch on the deepest mysteries of existence and reveal the intimate connection between time and the cosmos itself. For most of human history, time seemed eternal and unchanging. The cycles of day and night, the seasons, the stars, all seemed to repeat endlessly without beginning or end. But modern cosmology has revealed a very different picture. The universe itself appears to have had a beginning, a moment of creation that we call the Big Bang. And if time is woven into the fabric of space-time, then time itself might have begun with the birth of the universe. The Big Bang theory tells us that about 13.8 billion years ago, the universe was in a state of extremely high temperature and density. Space and time themselves came into existence at this moment, expanding and cooling to create the cosmos we observe today. This is not just the beginning of matter and energy, it's the beginning of the very arena in which matter and energy can exist. But what does it mean to say that time had a beginning? This question pushes us to the very limits of language and thought. We're accustomed to thinking of beginnings as events that happen in time. First, there was nothing. then there was something, but the beginning of time itself cannot be described. In this way, because there was no before for the beginning to happen in perhaps. A better way to think about it is that time is like the surface of a sphere. Just as the surface of a sphere is finite but has no edge or boundary, time might be finite but have no beginning or end in the usual sense. The beginning of time would be like the north pole of a sphere, a special point, but not a boundary or edge. This idea connects to some of the most advanced theories in cosmology. The no-boundary proposal, developed by Stephen Hawking and James Hartle, suggests that the universe is finite but unbounded in time, just as the surface of a sphere is finite but unbounded in space. In this model, asking what happened before the Big Bang is like asking what's north of the North Pole. The question itself is meaningless, but other theories suggest different possibilities. Some propose that the Big Bang was not the beginning of time, but rather a transition from a previous state. The universe might have existed in some form before the Big Bang, perhaps in a state of quantum superposition where all possible histories existed simultaneously. The Big Bang would then be the moment when this superposition collapsed into the definite history we observe. Another possibility is that time itself is cyclic. Some cosmological models propose that the universe undergoes infinite cycles of expansion and contraction, with each Big Bang followed by a big crunch, followed by another Big Bang. In these models, time would have no beginning or end, but would instead repeat in eternal cycles. The question of time's beginning is intimately connected to the quantum nature of reality. At the very beginning of the universe, the entire cosmos would have been smaller than a quantum particle, and quantum effects would have dominated its behavior. Understanding the beginning of time requires understanding how quantum mechanics applies to the universe as a whole. Some physicists propose that time emerges from quantum processes. In this view, the universe began in a timeless quantum state, and time crystallized out of this state as the universe evolved. Just as water freezes into ice when it reaches a certain temperature, time might have frozen out of a more fundamental, timeless reality. This idea connects to the concept of spontaneous symmetry breaking, which plays a crucial role in modern physics. Just as a perfectly symmetric situation can spontaneously break into an asymmetric state, the timeless symmetry of the early universe might have spontaneously broken to create the temporal asymmetry we observe today. The question of time's end is equally profound. If the universe continues to expand and cool, what will happen to time itself? Current observations suggest that the expansion of the universe is accelerating, driven by a mysterious force called dark energy. If this acceleration continues, the universe will eventually reach a state of heat death, where all matter and energy are uniformly distributed, and no more work can be done in this far future state. Time might lose its meaning without processes to mark the passage of time, without changes to distinguish one moment from another. The concept of time might become meaningless. The universe would exist in a state of eternal equilibrium, where nothing ever changes and time stands still. But even this scenario raises profound questions. What would it mean for time to stop? If time is fundamental to the nature of reality, can it really cease to exist? And if it can, what would remain? Some physicists propose that even in heat death, quantum fluctuations would continue to occur. These fluctuations might occasionally create brief moments of order and complexity. Like quantum mirages in a desert of equilibrium, time might not stop completely, but rather become sporadic and continuous. Another possibility is that the universe might undergo a phase transition that fundamentally changes the nature of time. Just as water can exist as solid ice, liquid, water, or gaseous steam, time might exist in different phases under different conditions. The heat death of the universe might be a transition to a different temporal phase, where time operates according to different rules. The study of time's beginning and end also reveals the deep connection between time and consciousness. Our ability to conceive of time's beginning and end is itself a remarkable feature of consciousness. We can imagine states of existence that transcend our own temporal experience, and we can contemplate the deepest questions about the nature of reality. This might not be a coincidence. Some philosophers propose that consciousness and time are intimately connected, that consciousness is what creates the experience of temporal flow, and that time is what makes consciousness possible. In this view, the questions of time's beginning and end are inseparable from questions about the nature of consciousness itself. The possibility that time had a beginning and might have an end also raises profound questions about the nature of existence. If time is finite, then every moment is precious and unique. Each instant represents a tiny fraction of the total temporal budget of the universe, never to be repeated. This perspective can be both humbling and inspiring. It reminds us that we are part of something much larger than ourselves, a cosmic drama that began with the Big Bang and will continue long after we're gone. But it also reminds us that we are active participants in this drama, contributing to the ongoing evolution of the universe through our choices and actions. Understanding the beginning and end of time also reveals the deep mystery of existence itself. Why does anything exist at all? Why is there something rather than nothing? These questions might be connected to the nature of time, perhaps existence, and time are so intimately connected that to ask why there is something rather than nothing is to ask why there is time rather than no time. As we contemplate these profound questions, we're reminded that our understanding of time is still evolving. The mysteries of time's beginning and end push us to the very limits of science and philosophy, challenging us to develop new concepts and new ways of thinking about the nature of reality. Perhaps the most important insight from studying time's beginning and end is that time is not just a container for events, but rather an active participant in the cosmic drama. Time is what makes change possible, what allows the universe to evolve from simple beginnings to complex structures, what enables the emergence of consciousness and meaning. In this sense, time is not just the stage on which the story of the universe unfolds, it is the story itself. The beginning of time is the beginning of all stories, and the end of time would be the end of all stories. Between these cosmic bookends, time creates the possibility for all the beauty, complexity, and meaning that we observe in the universe. As we near the end of our peaceful journey into the nature of time, let's take a moment to step back and appreciate the extraordinary symphony we've discovered. Time, we've learned, is not the simple, uniform flow that it appears to be in our everyday experience. Instead, it's a rich, complex, multifaceted phenomenon that reveals new layers of beauty and mystery. The deeper we explore, think of time as a vast symphony with multiple movements, each revealing different aspects of its nature. In the first movement, we encountered time as experience, the flowing stream of moments that carries us from past to future, the rhythm of our heartbeats, the cycle of days and seasons. This is the time of human life, the time of memory and anticipation, of growth and change and becoming. In the second movement, we discovered time as relativity, the flexible, dynamic dimension that can stretch and compress, that weaves together with space to form the fabric of reality itself. This is Einstein's time, where simultaneity is relative, where gravity curves the flow of moments, where twins can age at different rates depending on their motion through space-time. The third movement revealed time as quantum mystery, the uncertain, probabilistic domain where virtual particles borrow energy from the future, where entanglement creates instantaneous correlations across vast distances, where the very notion of precise temporal ordering becomes fuzzy and ambiguous. This is the time of the quantum realm, where reality itself seems to dance between possibility and actuality. In the fourth movement, we encountered time as information, the medium through which patterns and correlations flow, the dimension along which entropy increases and complexity emerges. This is the time of computation and communication, of Maxwell's demon and Landauer's principle, where the flow of time becomes inseparable from the processing of information that the fifth movement showed. Us time as creativity, the active force that enables novelty and emergence, that allows simple beginnings to blossom into complex beauty. This is the time of evolution and development, of star formation and galaxy growth, of consciousness and culture and art, and in the final movement, we contemplated time as mystery, the profound questions of beginning and end, of measurement and paradox, of the deep connections between time and existence itself. This is the time that pushes us to the very limits of understanding, that challenges our deepest assumptions about the nature of reality. Each of these movements is beautiful and profound in its own right, but what makes the symphony truly magnificent is the way they all harmonize together. Time is not just one thing or another, it's all of these aspects simultaneously. A multi-dimensional phenomenon that reveals different faces depending on how we approach it. The relativity of time doesn't contradict our experience of temporal flow, it enriches it, showing us that time is far more subtle and flexible than we ever imagined. The quantum uncertainty of time doesn't negate its arrow. It provides the fundamental randomness that enables creativity and emergence. The informational nature of time doesn't reduce it to mere computation. It reveals the deep connections between mind and cosmos, between consciousness and reality. This multifaceted nature of time reflects a deeper truth about reality itself. The universe is not a collection of separate, independent phenomena, but rather a unified whole in which every aspect reflects and connects to every other aspect. Time is not separate from space, matter is not separate from energy, mind is not separate from cosmos. Everything is interconnected in a vast web of relationships and processes. This holistic understanding of time has profound implications for how we live our lives. If time is creative, then every moment is an opportunity to participate in the universe's ongoing process of creation. If time is relational, then our connections with others and with the cosmos itself are not incidental features of our existence, but fundamental aspects of what it means to be real. If time is informational, then our thoughts and consciousness are not separate from the physical processes of the universe, but are integral parts of the cosmic information processing system. If time is mysterious, then there's always more to discover, always deeper layers of understanding to uncover. The symphony of time also reveals the deep interconnectedness of all knowledge. Physics and philosophy, science and spirituality, mathematics and mysticism all contribute different instruments to the grand composition. No single perspective can capture the full richness of time's nature. but together they create a harmony that is greater than the sum of its parts. This suggests that understanding time, like understanding any deep aspect of reality, requires a kind of intellectual humility. We must be willing to hold multiple perspectives simultaneously, to appreciate that truth is often paradoxical and multifaceted. The wave-particle duality of light, the complementarity of position and momentum in quantum mechanics, the relativity of simultaneity in space-time. All of these remind us that reality is richer and stranger than any single conceptual framework can capture. The symphony of time also reveals the importance of wonder and awe in the face of mystery. The deeper we probe into the nature of time, the more beautiful and mysterious it becomes. This is not a failure of understanding, but rather a sign that we're approaching something truly fundamental, something that connects to the deeper structures of existence itself. Wonder is not just an emotional response to mystery, it's a cognitive tool that opens our minds to new possibilities. When we approach time with wonder, we become more receptive to its subtle harmonies, more attuned to its hidden rhythms, more capable of appreciating its multifaceted beauty. Throughout our gentle exploration of what time is made of, we've discovered that time is not just an object of study, but also a profound teacher. The nature of time itself offers deep lessons about existence, consciousness, creativity, and meaning. As we reflect on these lessons, we begin to see how understanding time can transform our relationship with life itself. One of the most important lessons that time teaches us is the value of presence. In our exploration of the quantum nature of time, we discovered that the present moment is not just a thin slice between past and future, but rather the creative frontier where possibility becomes actuality. The present is where consciousness meets cosmos, where observation participates in the creation of reality itself. This understanding transforms our relationship with the present moment. Instead of seeing it as fleeting and insignificant, we can appreciate it as the most fundamental and important aspect of existence. The present is not just where we happen to be, it's where reality is being created, moment by moment, through the ongoing dance of quantum possibilities. Living with presence means recognizing that each moment is unique and irreplaceable. In the vast symphony of time, each instant plays its own unrepeatable note. To miss the present moment is to miss the very process by which existence unfolds. But presence is not about grasping or holding on to moments. That would be like trying to hold on to individual notes in a symphony. Instead, presence is about flowing with the music of time, participating fully in each moment while remaining open to what comes next. Another profound lesson that time teaches us is the nature of change. We've seen how time's arrow emerges from the increase of entropy, how complexity and beauty arise from the interplay of order and chaos, how creativity emerges from the balance between determinism and randomness. These insights reveal that change is not something that happens to us from outside, but rather the very medium in which we exist. Understanding the nature of change can help us develop a different relationship with the uncertainties and transitions in our lives. Instead of resisting change or fearing the unknown, we can appreciate change as the fundamental creative force of the universe. We are not separate from this creative process. We are expressions of it. This doesn't mean that change is always easy or pleasant. The second law of thermodynamics tells us that entropy increases, which means that all organized structures, including our bodies, our relationships, our institutions, are temporary. This can be a source of sadness and anxiety, but it can also be a source of profound appreciation for the preciousness of what we have. if everything is temporary, then nothing should be taken for granted. Every moment of health, every connection with another person, every experience of beauty or love or understanding is a gift that emerges from the creative chaos of existence and will eventually return to it. This temporality doesn't diminish the value of these experiences. It makes them infinitely precious. Time also teaches us about the nature of memory and identity. We've explored how memory is not a passive recording of the past, but an active reconstruction that happens in the present. This means that our sense of who we are is not fixed by our history, but is constantly being recreated through the ongoing process of remembering. This understanding can be deeply liberating if our identity is not locked in place by the past. Then we have the freedom to reimagine ourselves, to reconstruct our stories in ways that serve our growth and well-being. We are not prisoners of our history, but active participants in the ongoing creation of our identity at the same time. This reconstruction of memory and identity is not arbitrary. It's constrained by the physical traces of the past, by the web of relationships and commitments we've created, by the continuity of our embodied existence. We are free to reshape our identity, but this freedom operates within the larger patterns and structures of our lives. Time also teaches us about the nature of hope and possibility. We've seen how the quantum nature of reality means that the future is not completely determined by the past. There's genuine creativity, genuine novelty, genuine openness in the flow of time. This means that no matter how constrained our present circumstances might seem, there's always the possibility for something new to emerge. Hope is not just wishful thinking. It's recognition of the fundamental creativity of existence. The universe has been creating new forms and possibilities for billions of years, from the formation of atoms to the emergence of life to the evolution of consciousness. This creative process is not finished, it's ongoing, and we are part of it. But hope, based on understanding the nature of time, is different from naive optimism. It recognizes that creativity operates within constraints, that possibility is always bounded by actuality, that the future emerges from the present, rather than being imposed on it from outside. This kind of hope is more realistic and more resilient than false optimism. Time also teaches us about the nature of meaning and purpose. We've explored how consciousness plays a role in creating the temporal structure of experience, how our awareness participates in the ongoing evolution of the universe. This suggests that our lives are not meaningless accidents in an indifferent cosmos, but rather integral parts of the universe's ongoing process of self-creation and self-understanding. The meaning of our lives is not something that we have to impose on a meaningless universe from outside. Instead, meaning emerges from our participation in the cosmic process of creativity and consciousness. We find purpose not by escaping from time, but by participating more fully in its creative flow. This cosmic perspective on meaning doesn't diminish the importance of local concerns and personal relationships. Instead, it provides a larger context that enriches and deepens these connections. When we understand our intimate relationships as expressions of the fundamental interconnectedness of reality, they become not just personal pleasures, but cosmic events. Finally, time teaches us about the nature of death and continuity. We've seen how time itself might have a beginning and an end, how even the most fundamental structures of reality are temporary. This cosmic perspective on temporality can help us develop a more peaceful relationship with our own mortality. If time itself is temporary, then our own temporal existence is not an exception to the cosmic order, but an expression of it. We participate In the same creative process that gives rise to stars and galaxies, atoms and molecules, life and consciousness, our individual existence is temporary, but the creative process that we participate in is ongoing. This doesn't eliminate the reality of loss and grief, but it provides a larger context for understanding them. When we lose someone we love, we're experiencing the same temporal structure that governs all of existence. The pain of loss is real, but it's also a testament to the preciousness of the connections we've been able to form within the flowing stream of time. As we reach the culmination of our exploration into what time is made of, we arrive at a profound paradox that has echoed throughout our journey: the relationship between time and timelessness, between the flowing stream of moments and the eternal now that underlies all existence. Throughout our investigation, we've encountered hints of this paradox. In quantum mechanics, we discovered that entangled particles share instantaneous correlations that seem to exist outside of time. In relativity, we learned about the block universe where all moments exist simultaneously. In the study of consciousness, we found that awareness itself seems to transcend the linear flow of time. And in contemplating the beginning and end of time, we touched on realms that exist beyond temporal boundaries. These discoveries point toward a profound truth. While time is fundamental to our experience and to the operation of the physical universe, there's also something timeless that underlies and encompasses all temporal existence. This timeless dimension is not separate from time, but rather is the eternal ground from which time emerges and to which it returns. Think of it like the relationship between waves and the ocean. Each wave has its own temporal existence. It forms, crests, breaks, and disappears. But all waves are manifestations of the same underlying ocean, which exists in a sense beyond the temporal existence of any individual wave. Similarly, all temporal events might be manifestations of an underlying timeless reality. This timeless dimension is not emptiness or void, it's the fullness of pure potential, the pregnant silence from which all music emerges. It's what mystics throughout history have pointed toward when they speak of eternity, what physicists glimpse when they contemplate the quantum vacuum, what consciousness touches when it rests in pure awareness. Understanding this relationship between time and timelessness can profoundly transform our experience of existence. When we realize that the timeless is not somewhere else, but is the very ground of this moment, we can begin to taste eternity in the midst of time. The present moment is not just a fleeting instant in the stream of time. It's a doorway into the timeless. This doesn't mean that time becomes irrelevant or that we should try to escape from temporal existence. Rather, it means that we can learn to live in time while being rooted in the timeless. We can participate fully in the flowing stream of moments while remaining anchored in the eternal, now that is always present. This perspective transforms our relationship with both past and future. When we're rooted in the timeless present, we can remember the past without being bound by it, and anticipate the future without being anxious about it. Memory becomes a way of bringing the richness of experience into the present moment, and planning becomes a way of allowing the present to unfold into new possibilities. The recognition of the eternal now also transforms our understanding of death and birth. If we are fundamentally timeless beings having a temporal experience, then death is not the end of our existence, but rather a transition from one mode of being to another. Birth is not the beginning of our existence, but rather our emergence into temporal form from the timeless ground of being. This doesn't provide easy answers to the mysteries of existence, but it does provide a different framework for approaching them. instead of seeing ourselves as temporary accidents in an indifferent universe. We can understand ourselves as eternal beings participating in the cosmic dance of time and timelessness. The eternal now is also the realm of perfect understanding. In the flowing stream of time, our knowledge is always partial and evolving. We see aspects of truth, but never the whole. But in the timeless dimension, all perspectives are present simultaneously. The wave-particle duality of light, the complementarity of quantum mechanics, the relativity of simultaneity, all of these paradoxes are resolved in the eternal now, where all contradictions are reconciled. This perfect understanding is not something that we can achieve through effort or study. It's our fundamental nature, temporarily obscured by our immersion in the stream of time. When consciousness recognizes its own timeless nature, it realizes that it has always been what it was seeking. The seeker and the sought are one. The eternal now is also the realm of perfect peace. In the flowing stream of time, there's always movement, change, uncertainty. There's always something to achieve, something to avoid, something to worry about. But in the timeless dimension, there's perfect stillness and completeness. Nothing needs to be added or subtracted. Everything is already whole and perfect as it is. This peace is not the absence of activity, but rather the presence of perfect balance. It's like the eye of a hurricane, perfectly still while surrounded by tremendous activity. When we're rooted in this timeless peace, we can engage fully with the activities of temporal existence without being disturbed by their constant change. The eternal now is also the realm of unconditional love. In the flowing stream of time, love is often conditional, based on past experiences, future expectations, changing circumstances. But in the timeless dimension, love is the very fabric of existence itself. It's not something that we have to create or maintain, it's what we are at the deepest level. This timeless love encompasses all of existence without exception. It doesn't depend on worthiness or reciprocation. It's not diminished by mistakes or enhanced by achievements. It's the unconditional embrace of being itself, the recognition that everything that exists is a precious expression of the one underlying reality. Recognizing the eternal now doesn't require special knowledge or spiritual practices, though these can be helpful. It simply requires paying attention to what is already present in this moment. The timeless is not hidden somewhere else. It's the very nature of present awareness itself, right now. As you read these words, awareness is present. This awareness is not bound by time. It's the timeless witness of all temporal experience. Thoughts come and go in time, but the awareness of thoughts is itself timeless. Emotions arise and pass away in time, but the awareness of emotions is eternal. Even the body ages and changes in time, but the awareness of the body remains constant. This timeless awareness is not personal. It's the one universal consciousness that appears as all individual experiences. When we recognize our true nature as this timeless awareness, we realize that we are not separate beings struggling for survival in a hostile universe, but rather expressions of the one cosmic consciousness exploring itself through countless forms and experiences. The eternal now is the answer to the question, what is time made of? Time is made of eternity. It's the eternal expressing itself in temporal form, the timeless dancing as time, the one appearing as many. Understanding this transforms not just our intellectual understanding of time, but our lived experience of existence itself. In the eternal now, all questions are answered, not through explanation, but through direct recognition. What is time made? of it's made of this present awareness, this timeless presence, this eternal now that is always here, always available, always perfect and complete just as it is. Thank you for staying with me through this peaceful journey into what is. Time made of what we've discovered together is not just intellectual knowledge, but a doorway into a deeper way of being. Time, we've learned, is not just something that happens to us. It's something that we participate in creating through our very awareness and presence. As you continue on your own journey through time, I invite you to remember what we've explored together. Remember that each moment is a unique and precious note in the cosmic symphony. Remember that your consciousness is not separate from the fundamental creative processes of the universe. Remember that beneath the flowing stream of time lies the eternal now that is your deepest nature. The mystery of time is not something to be solved once and forgotten, but rather a living reality to be experienced and explored throughout your life. Each moment offers new opportunities to deepen your understanding, to participate more fully in the creative dance of existence, to recognize more clearly the timeless awareness that you are. May your exploration of time lead you not away from life, but deeper into its mystery and beauty. May your understanding of time's nature help you live with greater presence, deeper compassion, and more profound appreciation for the miracle of existence itself. And may you always remember that you are not just in time. Time is in you, expressing itself as your very being, creating itself as your very experience. In the end, the question, what is time made of, becomes, what are you made of? And the answer is the same: pure awareness, eternal presence, the timeless now that is the heart of all existence. You are time, and time is you, dancing together in the eternal symphony of being. Thank you for sharing this journey with me. The exploration of time's deepest nature is also an exploration of your own deepest nature. As you live your life in time, may you never forget the timeless truth of what you are. Until we meet again in the eternal now that is always present, I wish you peace, wonder, and the joy of endless discovery.